In 2024, China became the first nation to bring back soil from a place no human had ever touched. 1,935 grams of dust that could hold the key to powering entire civilizations. But here's what makes this discovery extraordinary. Buried within these far-side lunar samples lies helium-3, an isotope so rare on Earth that most people don't know it exists, yet so potentially transformative that it might just solve our planet's energy crisis forever. Stay with me until the end to discover why this handful of moon dust could change everything we envision about humanity's future, and why it might represent both humanity's greatest obstacle and its most promising opportunity. Now, grab a blanket, get comfortable, and prepare yourselves. We begin. Part 1. What China just brought home and why it could change everything. Imagine holding a handful of dust that could power entire cities, not metaphorically, literally. China's Chang'e 6 mission accomplished something no nation had ever attempted before. On June 25, 2024, their robotic explorer touched down on the moon's far side and collected 1,935.3 grams of soil and rock from the South Pole Aitken Basin. This wasn't just another sample return mission. This was humanity's first glimpse into a world that had remained hidden since the formation of our solar system. The far side of the moon is nothing like what we see when we glance up at night. While our familiar lunar companion shows us ancient lava flows that filled massive craters billions of years ago, the far side tells a different story entirely. Its crust runs thicker, older, scarred by impacts that dwarf anything we've witnessed on Earth. The highlands stretch endlessly, punctuated by sparse volcanic seas. Most intriguingly, this hemisphere may hold secrets to a completely different volcanic history than the side that perpetually faces us. But here's where the story becomes extraordinary. Among the materials locked within lunar soil exists helium-3, an isotope so rare on Earth that most people have never heard of it, yet so potentially powerful that some scientists believe it could revolutionize how we generate energy. While helium-3 remains practically non-existent in our atmosphere, the moon's surface has been collecting it for billions of years, deposited grain by grain through solar wind bombardment. China already knew this. Their earlier Chang'e 5 mission had measured helium-3 concentrations in near-side samples. They'd even identified a completely new phosphate mineral in those specimens, which they named Changesite Y. But the far side represented uncharted territory, both literally and scientifically. What exactly did Chang'e 6 sample during its 47-day mission? Volcanic soil that may have erupted during the moon's mysterious late-stage volcanic activity. Ancient impact materials blasted from depths we can barely imagine. Rocks that could rewrite our understanding of how the moon formed and evolved. These weren't random pickings from a cosmic sandbox. Each grain represents a carefully preserved record of processes that shaped not just the moon, but potentially influenced Earth's early development. Early laboratory analyses suggest something remarkable. The Chang'e 6 samples exhibit distinct characteristics that set them apart from all previously returned lunar materials. The far side soil appears significantly drier than typical near-side samples, with initial measurements indicating water concentrations below 1.5 micrograms per gram compared to the much higher concentrations found in some Apollo and Chang 5 specimens. But the differences extend far beyond water content. The first detailed analysis reveals that these specimens differ in some ways from those collected from the moon's near side, showing variations in mineral composition, grain size distribution, and space weathering characteristics that weren't anticipated based on orbital observations. The samples contain a higher proportion of impact-generated materials compared to volcanic fragments, reflecting the South Pole Aitken Basin's ancient collision history. Microscopic examination reveals that far-side regolith particles display different degrees of agglutination, the process by which individual mineral grains become welded together by impact-generated glass. This difference affects not just scientific understanding, but also practical considerations for future mining operations that must separate valuable materials from the complex mixture of impact debris and space-weathered fragments. The engineering achievement behind this sampling mission deserves recognition in its own right. Operating on the Moon's far side presents a challenge that sounds almost impossible. Since this hemisphere never faces Earth, radio signals cannot pass directly between mission control and any landed spacecraft. China solved this by positioning a relay satellite called Queqiao-2 at a gravitational balance point, allowing it to beam communications over the lunar limb. For the first time in human history, we had established a permanent communication bridge to the Moon's hidden face. Scientists worldwide are watching these samples with anticipation that borders on excitement. Far-side rocks could test fundamental theories about the Moon's formation during the solar system's chaotic early period. They might reveal how the lunar mantle differs from what we've learned through near-side exploration. Most importantly, they could answer questions about how long volcanic activity persisted on the far side, and whether that activity followed the same patterns we've documented on the visible hemisphere. The implications stretch far beyond academic curiosity. If lunar resources prove accessible and economically viable, the Moon could become humanity's first extraterrestrial industrial site. Water ice for life support and rocket fuel. Oxygen extracted from rock for breathing and propulsion. Metals for construction. And yes, potentially helium-3 for a new generation of clean fusion power. Yet for all the excitement surrounding these samples, we must remember that we're still in the earliest stages of understanding what they might tell us. The analyses have only just begun. The laboratory work will take years. The technological developments needed to actually utilize lunar resources remain decades away at minimum. What Chang'e 6 has truly accomplished is opening a door. Behind that door lies not just scientific knowledge, but potentially a fundamental shift in how humanity relates to space. The far side of the Moon is no longer a mystery glimpsed only through orbital reconnaissance. It has become a place we can touch, sample, and begin to understand. And sometimes, understanding is the first step toward transformation. Part 2. Helium-3, explained like I'm 5 picture, 2 children playing with building blocks. One child builds towers that occasionally fall down and make a mess. The other child builds towers that rarely fall, and when they do, they clean themselves up quickly. In the world of nuclear fusion, helium-3 is the well-behaved child. Helium-3 is a stable isotope of helium, meaning it contains 2 protons and just 1 neutron, unlike the common helium-4 we find in party balloons. This seemingly minor difference creates profound implications for nuclear fusion reactions. When helium-3 fuses with deuterium, a heavy form of hydrogen, the reaction produces fewer neutrons than traditional fusion approaches. Fewer neutrons means less radioactive contamination of reactor materials. Less radioactive contamination means safer, cleaner power generation. On Earth, helium-3 exists in quantities so small they're practically theoretical. Our planet's magnetic field and thick atmosphere shield us from most solar wind particles, preventing the steady accumulation that has occurred on the Moon for billions of years. The Moon lacks both magnetic protection and atmospheric filtering, making it an ideal collector of solar wind particles, including helium-3. The numbers reveal the staggering scale of what helium-3 extraction would actually require. To provide just 10% of Earth's projected energy demand by 2040, mining operations would need to process over 100 million tons of lunar regolith annually. That's equivalent to operating multiple large-scale terrestrial mining operations continuously, using equipment that somehow functions reliably in the vacuum of space, extreme temperature variations, and constant radiation bombardment. NASA studies have conceptualized mining systems that could excavate over 1,000 tons per hour using bucket wheel excavators adapted for lunar conditions. These machines would need to operate during the 14-day lunar day, processing hundreds of tons of regolith hourly while heating the material to several hundred degrees Celsius to release trapped gases. The energy requirements alone would demand massive solar arrays or nuclear reactors just to power the extraction process. The engineering challenges multiply at every step. Lunar regolith consists of extremely fine, abrasive particles that carry electrostatic charges from solar wind bombardment. This dust adheres to everything, clogs mechanical systems, and gradually erodes equipment surfaces. Mining machinery would need constant maintenance and replacement of worn components, all performed by robotic systems since human workers couldn't survive extended exposure to the lunar environment. Gas separation systems must isolate helium-3 from the mixture of hydrogen, helium-4, nitrogen, and other volatile components released during regolith heating. This requires sophisticated chemical processing equipment that can operate reliably in vacuum conditions while handling corrosive gases and maintaining precise temperature and pressure controls. The purified helium-3 must then be compressed, stored, and either used locally or transported back to Earth for fusion reactor applications. China's Chang'e 5 samples provided the first direct measurements of helium-3 content in returned lunar material, offering scientists baseline data for understanding how these concentrations vary across different lunar terrains. Now Chang'e 6 adds crucial far-side context to that picture, potentially revealing whether the hidden hemisphere harbors different resource profiles than what we've studied on the near side. Here's where we enter clearly speculative territory. Advocates of helium-3 fusion paint an almost utopian picture of energy abundance. They suggest that if future reactors could successfully use deuterium-helium-3 fuel, a small mass of this exotic material could power entire nations while producing minimal nuclear waste. The numbers sound almost magical. Some estimates suggest that 100 tons of helium-3 could satisfy Earth's energy needs for an entire year. Reality check number 1. We don't yet have working fusion power plants, even using the supposedly easier deuterium-tritium fuel combination that researchers have pursued for decades. Helium-3 fusion would be significantly more challenging and likely requires technologies we haven't developed yet. The reactor conditions needed to initiate and sustain helium-3 fusion are more extreme than those required for conventional approaches. Reality check number 2. Mining helium-3 at parts per billion concentrations would demand massive robotic mining operations, high-temperature processing facilities to release trapped gases from mineral grains, and a complete logistical infrastructure either to utilize the fuel directly on the Moon or transport it back to Earth. We're talking about industrial operations that dwarf anything currently operating in terrestrial mining. Reality check number 3. Many fusion experts argue that helium-3 represents a second or third generation fusion technology that might become relevant only after we've successfully mastered deuterium-tritium reactions and built a thriving fusion energy industry. The economics of helium-3 extraction and utilization remain highly uncertain, especially when compared to the abundant deuterium and lithium available on Earth for first-generation fusion approaches. Yet, despite these sobering realities, helium-3 continues to matter in today's space exploration discussions. The possibility of revolutionary energy technology motivates continued lunar exploration, pushes development of mining robotics and in-situ resource utilization techniques, and keeps transformative clean energy visions alive in public consciousness. Sometimes the journey toward an ambitious goal proves more valuable than reaching the destination itself. Chang'e 6 could contribute valuable data to future helium-3 prospecting efforts by mapping how far-side soils differ from near-side deposits, identifying which minerals serve as the best helium-3 hosts, and understanding the thermal history that affects how effectively different lunar regions retain solar wind gases. This information won't make helium-3 fusion practical tomorrow, but it builds the knowledge base that future generations might need if they choose to pursue this path. The honest way to discuss helium-3 in any documentary is to present it as a compelling hope coupled with significant technological and economic hurdles. The vision deserves respect because it represents humanity's perpetual drive to solve energy challenges through innovation. The hurdles deserve acknowledgement because overpromising technological timelines has historically undermined public confidence in legitimate scientific endeavors. Chang'e 6 has brought us one small step closer to understanding whether the Moon might someday contribute to solving Earth's energy challenges. Whether that contribution involves helium-3, water for hydrogen fuel, solar power beamed from lunar installations, or resources we haven't yet imagined, remains an open question. What's certain is that we won't find answers without first asking the right questions and gathering the data needed to answer them responsibly. Part 3. What makes the far side special? The Moon wears two faces, and we've been seeing only one of them for all of human history. What lies on the far side isn't just geographically different from our familiar lunar companion. It's fundamentally, mysteriously, almost impossibly different. The far side's crust runs thicker than the near side, in some places more than twice as thick. While the near side averages around 60 kilometers of crustal material, far side regions can exceed 120 kilometers of solid rock between the surface and the lunar mantle below. This isn't a subtle difference. It's a geological divide that suggests the two hemispheres experienced completely different evolutionary histories. Where our familiar Moon shows dark patches called Maria, ancient lava flows that filled massive impact craters, the far side presents mostly bright highlands. These highlands preserve some of the oldest rocks in the solar system, materials that formed during the Moon's initial solidification over 4 billion years ago. While near-side Maria cover roughly 30% of that hemisphere's surface, far-side Maria account for less than 2% of the hidden hemisphere. Chang'e 6 touched down in perhaps the most significant feature on the Moon's far side, the South Pole, Aitken Basin. This impact scar represents one of the largest and oldest confirmed impact structures in our entire solar system. The collision that created this basin occurred so early in lunar history that studying its excavated materials offers insights into the Moon's deep interior composition and the violent bombardment period that shaped all terrestrial planets. Early laboratory work on Chang'e 6 samples is revealing intriguing differences. The far-side soils from this landing site appear notably drier than many near-side samples analyzed previously. This observation, while preliminary and based on limited sample processing, suggests that the two hemispheres may have experienced different histories of water delivery, retention, and loss. Understanding these differences could revolutionize models of how volatile materials behave on airless planetary bodies. China's earlier far-side rover, Yutu-2, already provided tantalizing hints about what makes this hemisphere special. The rover identified materials interpreted as mantle-derived rocks, olivine and pyroxene minerals that typically form deep within planetary bodies. These materials were apparently excavated and scattered across the surface by the massive impact that created the South Pole Aitken Basin, offering scientists direct access to lunar interior materials without requiring deep drilling operations. The far side has also surprised scientists with unexpected volcanic features. The Compton-Belkovich complex represents rare silicic volcanism on the lunar surface, producing rocks with unusual chemical compositions that don't match typical lunar basalts. This type of volcanism is common on Earth, but extremely rare on the Moon, suggesting that far-side geological processes followed paths that diverged significantly from near-side evolution. Orbital mapping missions have documented how thoroughly the near and far sides differ in their fundamental characteristics. Thorium concentrations, which trace the distribution of a rock type called creep, show dramatically different patterns between the hemispheres. Creep rocks, rich in potassium, rare earth elements, and phosphorus, concentrate heavily on the near side but remain relatively scarce on the far side. This distribution has profound implications for understanding how the Moon's magma ocean solidified and differentiated during its formation. These differences matter enormously for future resource utilization efforts. Helium-3 retention correlates with regolith maturity, titanium-rich mineral content, surface temperature, and solar wind exposure. all factors that vary systematically between the near and far sides. Future mining operations will need detailed resource maps that account for these hemispheric differences to identify the most promising extraction sites. From a pure science perspective, far-side samples help fill critical gaps in our understanding of lunar volcanic history. Near-side samples collected by Apollo missions and lunar probes, supplemented by Chang'e 5 materials, have provided detailed records of volcanic activity on the visible hemisphere. But we've lacked comparable data from the far side to determine whether volcanic processes occurred simultaneously across both hemispheres or followed independent timelines. Chang'e 6 samples could reveal precise ages for far-side volcanic episodes, identify the mantle sources that fed far-side magmas, and document the impact history that shaped this hemisphere's unique topography. They'll also enable scientists to quantify how space weathering processes, the gradual alteration of surface materials by solar wind and micrometeorite bombardment, differ between environments that face Earth and those that remain perpetually hidden. The far side represents more than just another place to explore. It's a natural laboratory that preserved different aspects of lunar and early solar system history. While the near side shows us one version of how rocky planets evolve, the far side offers an alternative narrative shaped by different impact histories, volcanic processes, and resource distributions. What makes the far side truly special isn't just its mystery, but its promise. It's the same moon we've always known, yet completely different. Same origin story, different plot development. And now, for the first time, we're beginning to read both chapters of the lunar story simultaneously. Part 4. How China pulled off a far-side sample return. Imagine trying to direct a complex surgical operation while standing behind a solid wall, unable to see the patient or communicate directly with your surgical team. That's essentially what operating on the moon's far side requires, and China just performed the most intricate procedure in space exploration history. The fundamental challenge sounds almost insurmountable. The moon's far side never faces Earth due to tidal locking, the same gravitational phenomenon that keeps one face of the moon perpetually visible to us. This means radio signals cannot travel directly between Earth and any spacecraft operating on the hidden hemisphere. For decades, this communication blackout made far-side exploration seem practically impossible. China's solution required unprecedented planning and precision. They launched Queqiao-2, a specialized relay satellite, positioning it at the second Earth-Moon Lagrange point, a gravitational balance point approximately 65,000 kilometers beyond the Moon. From this position, the satellite maintains constant line-of-sight contact with both Earth and the Moon's far side, creating humanity's first permanent communication bridge across the lunar limb. The Chang'e 6 mission itself involved a sophisticated 4-part spacecraft stack. The lander component handled touchdown operations and sample collection. An ascender module was designed to blast off from the lunar surface carrying precious cargo. An orbiter remained in lunar orbit to receive samples from the ascending vehicle. Finally, a re-entry capsule would transport materials safely back to Earth's surface. Mission planners selected their touchdown zone with extraordinary care. They needed a site within the South Pole Aitken Basin that offered both scientific value and operational safety. The chosen location contained both volcanic materials from ancient lava flows and impact materials excavated by the Bayesian-forming collision, providing maximum scientific diversity within a single landing site. The terrain had to be smooth enough for safe landing while remaining geologically interesting enough to justify the mission's complexity. Chang'e 6 aimed to collect multiple sample types during its surface operations. Surface scooping would gather materials representing the uppermost regolith layer, while drilling operations would access subsurface materials potentially less modified by space weathering processes. This sampling strategy maximized the chances of obtaining specimens that represent different geological processes and time periods. The sample collection and return sequence required flawless execution with no possibility for real-time troubleshooting. Once the ascender blasted off from the far side, it had to rendezvous with the orbiting spacecraft, transfer samples to the return capsule, and begin the journey home. Any malfunction during these critical phases would result in total mission failure. When the sample container finally opened in Beijing laboratories, scientists discovered 1,935.3 grams of lunar material with unexpectedly interesting physical properties. The samples included clumps of soil with stickier textures than some previous lunar returns, possibly indicating different space weathering conditions or volcanic glass content that affects how individual grains adhere to each other. These textural differences aren't merely curious. Space weathering processes, the gradual alteration of surface materials by solar wind bombardment and micrometeorite impacts, create glassy coatings and welded aggregates that can dramatically affect how regolith behaves during mining operations. Understanding these properties becomes crucial for designing future extraction equipment. The Chang'e 6 mission establishes a technological blueprint that enables far more ambitious far-side operations. China's planned Chang'e 7 and Chang'e 8 missions will test resource utilization technologies and construction techniques needed for their International Lunar Research Station concept. The relay-first approach pioneered by Keqiao 2 makes such permanent installations feasible for the first time. Previous Chinese far-side exploration already demonstrated how direct ground truth observations resolve orbital mysteries. The Chang'e 4 lander and Yutu-2 rover investigated a gel-like substance that generated widespread speculation online. Detailed analysis revealed it was simply impact melt glass, a common product of meteorite strikes. Similarly, the so-called mystery hut that captured internet attention turned out to be an ordinary boulder viewed from a distance that created an optical illusion. These examples illustrate why sample return missions matter so profoundly. Orbital observations and rover investigations can identify interesting features and suggest possible explanations, but only laboratory analysis of actual samples can provide definitive answers about composition, age, and formation processes. Chang'e 6 represents more than technological achievement. It demonstrates that patient engineering, combined with systematic problem-solving, can overcome barriers that initially seem impossible. The relay satellite approach, the precision landing techniques, the robotic sample collection and return procedures all required innovations that expand humanity's operational capabilities throughout the solar system. The mission's success validates China's methodical approach to lunar exploration, building capabilities incrementally through increasingly complex missions rather than attempting everything at once. This philosophy differs markedly from the Apollo program's rapid, high-risk approach, but it offers advantages in terms of sustainability and technological development. What China accomplished with Chang'e 6 will enable far-side exploration by other nations and organizations. The communication relay techniques, landing procedures, and operational methods can be adapted and improved by future missions. In space exploration, every successful mission creates infrastructure and knowledge that benefits all subsequent efforts. Part 5. What these far-side samples might tell us. Next, laboratory analysis of Chang'e 6 samples is just beginning, but the questions these materials might answer could reshape our fundamental understanding of how rocky planets form and evolve. Each grain of far-side soil contains information encoded over billions of years, waiting for the right analytical techniques to decode its secrets. Dating far-side basalts and impact glasses will determine how long volcanic activity persisted on the hidden hemisphere. Near-side samples have revealed that major volcanic episodes occurred primarily between 3 and 4 billion years ago, with some younger activity extending to perhaps 2 billion years ago. But we know virtually nothing about far-side volcanic timelines. Did volcanism occur simultaneously on both hemispheres, or did different thermal and compositional conditions create independent evolutionary paths? Water content measurements could confirm whether far-side soils are genuinely drier than near-side materials, as preliminary analyses suggest. This isn't merely an academic question about lunar hydration. Water distribution affects everything from future resource utilization to understanding how volatile materials behave on airless worlds throughout the solar system. If hemispheric differences in water retention are confirmed, they could revolutionize models of how planetary bodies acquire and lose volatile compounds. Chang 6 samples might yield entirely new lunar minerals, following the precedent set by Chang 5's discovery of Changesite Y. The Moon's chemical diversity remains poorly understood, particularly for the far side, where different impact histories and magmatic processes may have produced mineral assemblages not seen in near-side samples. New minerals aren't just scientific curiosities. They can indicate previously unknown geological processes or environmental conditions. Space weathering analysis will quantify how solar wind bombardment and micrometeorite impacts affect materials differently between the hemispheres. The far side experiences slightly different cosmic ray exposure and solar wind conditions compared to the near side, potentially creating distinct alteration patterns in surface materials. Understanding these differences becomes crucial for interpreting orbital remote sensing data and planning future surface operations. Mantle composition studies could test whether the South Pole Aitken impact truly excavated deep lunar interior materials, as suggested by earlier rover observations. If Chang 6 samples contain olivine and pyroxene signatures consistent with mantle derivation, they would provide unprecedented insights into the Moon's internal structure and differentiation processes. This information could help resolve long-standing debates about lunar formation and early evolution. Helium-3 measurements in far-side samples will add crucial data points to resource assessment efforts. Scientists will measure not just helium-3 concentrations, but also identify which mineral phases serve as the most effective host materials. Ilmenite, a titanium iron oxide mineral, is particularly important because it efficiently retains solar wind gases while remaining relatively easy to process at elevated temperatures. Magnetic and radiation history locked within tiny glass spherules could provide records of ancient solar wind conditions extending back billions of years. These microscopic time capsules preserve information about how the Sun's radiation environment changed over geological time, offering insights relevant to understanding stellar evolution and its effects on planetary atmospheres. Volcanic source analysis will determine whether far-side magmas originated from mantle sources similar to those that fed near-side volcanism, or whether hemispheric differences in crustal thickness and composition created distinct magmatic systems. Trace element signatures in volcanic minerals can reveal the temperature, pressure, and chemical conditions under which far-side lavas formed. Impact gardening rates, the frequency with which meteorite bombardment churns and mixes surface materials, vary significantly across the lunar surface depending on location and geological age. Chang 6 samples will help quantify these processes for the far side, information that's essential for any future mining operation that must account for how quickly surface deposits get mixed and redistributed. Ground truth calibration of orbital remote sensing data represents another crucial application for Chang 6 samples. Spacecraft observations can identify interesting locations and estimate mineral abundances, but only direct sample analysis can provide the accuracy needed to validate and refine these remote measurements. Future missions will use this calibrated data to select landing sites and plan operations with much greater confidence. The analytical work ahead will take years to complete. Sophisticated instruments at laboratories worldwide will measure isotopic compositions, mineral structures, chemical abundances, and physical properties with precision that exceeds what's possible during space missions. Each analytical technique provides different types of information, and the full story emerges only when multiple approaches are combined and cross-verified. International collaboration in sample analysis ensures that the scientific benefits extend far beyond any single nation's research capabilities. Chang 6 samples will be studied by researchers from multiple countries, bringing diverse expertise and analytical approaches to bear on common questions. This collaborative approach has historically produced the most comprehensive and reliable scientific results. The questions that Chang 6 samples might answer extend far beyond lunar science. Understanding how the Moon formed and evolved provides crucial constraints on models of terrestrial planet formation throughout the galaxy. The processes that shaped our Moon likely influenced Earth's early development and may be common to rocky planet formation everywhere. Part 6. Is there water on the Moon? The question isn't whether water exists on the Moon anymore. The question is how much, where it hides, and what we can do with it. The answer to that first question fundamentally changed in 2009, when NASA's L-Cross mission deliberately crashed into Cabeus crater near the lunar South Pole and detected water ice in the debris cloud kicked up by the impact. That same year, India's Chandrayaan-1 mission carried NASA's Moon Mineralogy Mapper, an instrument that detected signatures of water molecules and hydroxyl groups spread across lunar high latitudes. These weren't isolated deposits hiding in a few crater shadows. Water chemistry appeared distributed much more widely across the lunar surface than anyone had expected. But detecting water signatures from orbit is different from measuring actual water concentrations in soil samples. China's Chang'e 5 mission provided the first direct measurements of water content in returned lunar materials, finding approximately 120 parts per million water in one analyzed rock. Most of this water came from solar wind implantation, hydrogen atoms from the sun combining with oxygen atoms in lunar minerals to form water molecules trapped within crystal structures. Now Chang'e 6 samples are revealing how water distribution differs between the hemispheres. Early analyses suggest far-side soils from the South Pole Aitken Basin contain significantly less water than many near-side samples, with concentrations below 1.5 micrograms per gram. This difference isn't just academically interesting, it indicates that geology matters enormously for understanding where future water resources might be accessible. The most concentrated water deposits exist as ice in permanently shadowed craters near the lunar poles. These regions never receive direct sunlight, maintaining temperatures cold enough to preserve water ice for billions of years. NASA's calculations suggest these polar cold traps contain substantial amounts of frozen water, potentially billions of tons distributed across numerous crater locations. For future astronauts and robotic missions, lunar water represents far more than just drinking water, though it certainly includes that application. Water can be split into hydrogen and oxygen through electrolysis, providing breathable air for life support systems and propellant components for rockets. Oxygen and hydrogen combustion produces tremendous thrust while generating only water vapor as exhaust, making it an environmentally clean propulsion system. Water also serves crucial industrial functions that become important for permanent lunar installations. It can provide radiation shielding when frozen into blocks or contained within habitat walls. It serves as a coolant for thermal management systems and as a working fluid for various mechanical and chemical processes. In many ways, water becomes the fundamental resource that enables other resource utilization activities. However, it's crucial to understand what lunar water isn't. It's not lakes and rivers and familiar terrestrial water sources. Lunar water exists primarily as ice deposits in extremely cold locations and as trace amounts bound within mineral structures. Accessing these resources requires sophisticated equipment to either mine ice from crater shadows or extract trace water from processed regolith. The distribution of lunar water follows patterns that reflect the Moon's complex environmental history. Polar regions accumulate the most ice because cold trapped temperatures prevent sublimation back to space. Equatorial regions contain mainly trace water from solar wind implantation, while mid-latitudes show intermediate characteristics depending on local geology and thermal history. Chang'e 6 adds a new chapter to the lunar water story by providing the first far-side water measurements from returned samples. If far-side soils prove systematically drier than near-side materials, it suggests that hemispheric differences in crustal composition, impact history, or thermal evolution significantly affect water retention processes. Understanding lunar water distribution requires thinking about multiple sources and loss mechanisms operating over billions of years. Comets and asteroids delivered water during the heavy bombardment period early in solar system history. solar wind hydrogen continues to implant into surface materials, creating new water through chemical reactions. Meanwhile, solar heating, micrometeorite impacts, and cosmic ray interactions constantly remove water from surface materials. The Moon's lack of atmosphere means that water molecules at the surface can escape directly to space unless they're trapped in cold locations or bound within mineral structures. This creates a complex redistribution system where water migrates from warmer regions toward polar cold traps over geological timescales. Future water prospecting missions will build on the foundation established by orbital surveys and sample return missions like Chang'e 6. Detailed maps of water distribution will guide landing site selection for both human missions and robotic mining operations. The most valuable locations will offer multiple resources in close proximity: water for life support, oxygen for breathing, metals for construction, and favorable terrain for landing and operations. The honest assessment of lunar water resources suggests there's enough to matter for exploration and industrial activities, but extraction and utilization will require substantial infrastructure development. We're not talking about simply drilling wells and pumping water to the surface. Lunar water extraction demands heated processing facilities, electrolysis equipment, gas separation systems, and storage infrastructure that can operate in the extreme lunar environment. Chang'e 6 samples provide one more piece of the lunar water puzzle, helping scientists understand how this crucial resource varies across different geological settings. Whether that variation ultimately helps or complicates future utilization efforts remains to be determined through continued analysis and exploration. Part 7. Mining the Moon. The beginner's guide. Mining on the Moon sounds like science fiction, but the basic concepts are surprisingly straightforward. Extract oxygen from common minerals. Collect water ice from crater shadows. Process regolith into construction materials. The challenge isn't understanding what to do, it's engineering systems that can do it reliably in one of the harshest environments humans have ever encountered. In situ resource utilization, mercifully abbreviated as ISRU, represents the foundation of sustainable lunar operations. Instead of shipping everything needed from Earth at enormous cost, ISRU enables missions to live off the land, extracting and processing local materials for life support, propellant, and construction applications. The Moon offers abundant raw materials for these purposes, but accessing them requires specialized equipment and substantial energy inputs. Oxygen extraction from lunar minerals provides perhaps the most straightforward ISRU application. Many common lunar rocks contain metal oxides, particularly ilmenite, a titanium iron oxide mineral that can be processed to release both oxygen and useful metals. Heating ilmenite to temperatures around 1000 degrees Celsius in the presence of hydrogen causes reduction reactions that liberate oxygen gas while producing water vapor and metallic iron. Helium-3 extraction involves much more complex processes, but the basic principles are well understood. Lunar regolith must be heated to several hundred degrees Celsius to release implanted solar wind gases, including helium-3 along with hydrogen, helium-4, nitrogen, and other volatile components. Gas separation and purification systems then isolate helium-3 from the mixture, concentrating it for storage and eventual use. The scale requirements for helium-3 extraction reveal why this resource remains speculative for near-term applications. Processing 150 tons of regolith to extract a single gram of helium-3 demands massive industrial equipment, enormous energy inputs, and handling systems capable of processing regolith continuously over extended periods. Current mining technology would need dramatic advances in automation and efficiency to make such operations economically viable. Powering lunar mining operations presents its own engineering challenges. Solar arrays work well during the 14-day lunar day, but provide no energy during the equally long lunar night. Polar locations near permanently shadowed regions offer nearly continuous solar exposure on crater rims, while providing access to water ice deposits in adjacent shadows. Nuclear reactors could provide steady power regardless of solar conditions but add complexity and regulatory challenges. Manufacturing on the Moon using local materials could dramatically reduce the cost of lunar operations. Three-dimensional printing with regolith-based materials can produce landing pads, habitat foundations, radiation shielding, and even complex mechanical components. The Moon's low gravity and lack of atmosphere actually simplify some manufacturing processes while complicating others, requiring entirely new approaches to industrial operations. Resource mapping becomes crucial for planning efficient mining operations. High titanium mare basalts offer the best helium-3 concentrations but may not coincide with optimal locations for solar power or Earth communications. Polar ice deposits provide essential water resources but exist in permanently shadowed regions that complicate equipment operations and maintenance. Future mining sites will need to balance resource accessibility with operational practicality. Robotic mining systems will likely precede human operations by years or decades. Autonomous equipment must handle unpredictable conditions, perform maintenance on itself, and operate reliably for extended periods without Earth-based intervention. The communication delays inherent in Earth-Moon operations mean that real-time control is impossible. Mining robots must make decisions independently based on programmed parameters and artificial intelligence systems. Environmental considerations matter even on the seemingly lifeless Moon. Dust control becomes critical both for equipment reliability and human health. Mining operations could potentially disturb scientifically valuable sites or interfere with radio astronomy observations on the lunar far side. International agreements will likely establish protected zones and operational guidelines to minimize conflicts between different types of lunar activities. The economics of lunar mining depend on factors that remain highly uncertain. Launch costs from Earth continue declining due to reusable rocket technology, but they're still measured in thousands of dollars per kilogram. Lunar manufacturing could eventually produce goods that are cheaper to use in space than equivalent items launched from Earth, but the infrastructure required to reach that point represents massive upfront investments. Some resources make more economic sense for lunar use rather than Earth export. Rocket propellant produced on the Moon could fuel missions throughout the solar system without requiring expensive launches from Earth's surface. Construction materials for space habitats and solar power satellites might be more economically sourced from the Moon than from terrestrial mining operations, especially for projects intended for use in space. Helium-3 occupies a unique position in lunar resource discussions because its value depends entirely on technological developments that haven't occurred yet. If fusion power using helium-3 becomes practical and economically competitive, the Moon could become humanity's primary energy source. If fusion follows other technological paths, or if helium-3 fusion proves impractical, this resource might remain a scientific curiosity rather than an economic driver. Change 6 samples contribute to lunar mining feasibility studies by providing ground truth data about far-side resource concentrations and processing characteristics. Understanding how helium-3, water, and other valuable materials vary across different lunar terrains helps mission planners identify the most promising locations for future operations and estimate the infrastructure requirements needed to make lunar mining successful. Part 8. The New Moon Rush. USA, India, Japan, private players. The Moon is experiencing its busiest period since the 1970s, but this time the players, motivations, and technologies are completely different. Where the original space race involved two superpowers competing for prestige and strategic advantage, today's lunar renaissance includes multiple nations, private companies, and international partnerships pursuing diverse, scientific, economic, and strategic objectives. NASA's Artemis program represents America's return to human lunar exploration, though the timeline has shifted significantly from original projections. Artemis 2, the first crewed mission around the Moon since Apollo 17, is now scheduled no earlier than 2025 or 2026. Artemis 3, which aims to land the first humans on the Moon since 1972, has moved to no earlier than 2027. These delays reflect the genuine complexity of developing new spacecraft, spacesuits, and landing systems that meet modern safety standards. The United States achieved a significant milestone in February 2024 when Intuitive Machines' IM-1 lander became the first American spacecraft to soft land on the Moon since Apollo. Despite tipping over after touchdown due to landing gear issues, the mission successfully demonstrated commercial lunar delivery capabilities and transmitted valuable scientific data back to Earth. This success validated NASA's Commercial Lunar Payload Services program, which contracts private companies to deliver instruments and experiments to the lunar surface. India's Chandrayaan-3 mission in 2023 marked another major achievement in global lunar exploration. The spacecraft executed a precision landing near the Moon's south polar region, demonstrating advanced navigation and hazard avoidance technologies. The mission's rover confirmed the presence of sulfur in lunar soil and transmitted detailed images of the local terrain, contributing valuable data to international lunar science efforts. Japan's SLIM mission, the Smart Lander for Investigating Moon, accomplished its primary objective of demonstrating pinpoint landing technology with unprecedented precision. The spacecraft touched down within approximately 100 meters of its target location, a navigational feat that enables future missions to access scientifically valuable sites that were previously too risky to attempt. SLIM also deployed Sora-Q, a tiny transformable rover that captured images of the lander and surrounding terrain. China's lunar exploration roadmap extends well beyond Chang'e 6, with ambitious plans for Chang'e 7 and Chang'e 8 missions that will test resource utilization technologies and construction techniques needed for their proposed International Lunar Research Station. This facility represents an alternative to the Artemis Accords framework, offering participating nations a different path for lunar exploration and development under Chinese leadership. The multiplication of lunar missions serves purposes far beyond national prestige. Every successful touchdown improves navigation algorithms, hazard avoidance systems, communication protocols, and sampling techniques that benefit all future missions. The Moon is becoming humanity's testing ground for technologies and operational procedures that will eventually enable exploration throughout the solar system. Private companies are playing increasingly important roles in this new lunar economy. Beyond payload delivery services, companies are developing lunar rovers, habitat modules, mining equipment, and communication systems that governments can purchase rather than develop internally. This commercial approach potentially reduces costs and accelerates development timelines by leveraging competitive markets and private investment. The lunar South Pole has emerged as the primary target for multiple nations and organizations. This region offers several advantages: potential water ice deposits in permanently shadowed craters, nearly continuous solar exposure on crater rims for power generation, and reasonable communication access to Earth. The convergence of multiple missions toward polar regions creates both opportunities for collaboration and risks of interference. International competition is driving faster progress in lunar technologies, but it's also creating coordination challenges. Multiple missions operating in similar timeframes and locations require careful scheduling to avoid radio interference, landing hazards, and contamination of scientific sites. The lack of comprehensive international coordination mechanisms for lunar surface operations represents a growing challenge as activity levels increase. NASA's Commercial Lunar Payload Services program has contracted multiple companies to deliver scientific instruments and technology demonstrations to various lunar sites. These missions serve as precursors to human exploration, testing equipment and procedures under actual lunar conditions while providing valuable scientific data. The program's success demonstrates how government agencies can leverage commercial capabilities to achieve exploration objectives more efficiently. The technological advances demonstrated by recent missions are remarkable. Hazard avoidance systems can now identify and avoid boulders, craters, and slopes during landing sequences. Communication relay capabilities enable operations on the lunar far side. Sample collection and return systems operate autonomously over extended periods. Navigation systems achieve precision landing within meters of target locations. What makes this era different from the Apollo period is sustainability. Where Apollo focused on achieving rapid success at enormous cost, current programs emphasize building infrastructure and capabilities that can support long-term presence and utilization. The goal isn't just to visit the moon again, but to establish permanent human and robotic operations that expand over time. The diversity of participants also creates resilience in ways the Apollo era lacked. If any single program encounters technical difficulties or funding challenges, other programs continue advancing lunar capabilities. Multiple independent approaches to similar challenges increase the likelihood that practical solutions will emerge, even if specific missions encounter problems. Looking ahead, the next few years will determine whether this renewed lunar activity leads to sustainable presence or follows the Apollo pattern of initial success followed by withdrawal. The key difference may be whether lunar operations can demonstrate clear economic value through resource utilization, scientific discovery, or strategic advantages that justify continued investment over political and economic cycles. Chang'e 6 fits into this broader context as one mission among many, but its focus on far-side sample return provides unique scientific value that benefits the entire international community. The samples collected by China will be studied by researchers worldwide, contributing to the knowledge base that guides future exploration decisions by all spacefaring nations. Part 9. Apollo to Chang'e, 50-plus years of lunar sample surprises. The story of lunar samples is a story of constantly overturned assumptions, beginning with the very first rocks that Neil Armstrong and Buzz Aldrin collected from the Sea of Tranquility in 1969. Scientists expected lunar material to resemble terrestrial rocks, perhaps with some interesting differences due to the lack of atmospheric weathering. Instead, they discovered materials unlike anything on Earth. Apollo and lunar missions revealed that most lunar volcanic activity occurred between 3 and 4 billion years ago, during a period when the moon was still hot enough to sustain widespread magma generation. The samples showed clear evidence of an ancient magma ocean that had crystallized and differentiated, creating the highland rocks and mare basalts that define the lunar surface we observe today. This timeline suggested that the moon had been geologically dead for billions of years. Then Chang'e 5 shattered that assumption. Samples returned from Oceanus Procellarum in 2020 contained basaltic rocks with radiometric ages of approximately 2 billion years, extending the moon's volcanic lifespan by 8 to 900 million years beyond what Apollo samples had indicated. This discovery forced scientists to reconsider fundamental models of lunar thermal evolution and magma generation. Chang'e 5 also provided the first in-situ measurements of water content in lunar samples, detecting approximately 120 parts per million water in analyzed rocks. Most of this water originated from solar wind implantation, but the measurement confirmed that lunar materials retain more water than previously thought and demonstrated techniques for measuring water content in future returned samples. The Chang'e 5 mission yielded another surprise, the discovery of changesite, Y, a new phosphate mineral never before identified in terrestrial or meteorite samples. This mineral contains elements and crystal structures that formed under conditions unique to the lunar environment, expanding our understanding of planetary mineralogy and the chemical processes that occur on airless worlds. Now Chang'e 6 samples could reveal whether the far side experienced similar late-stage volcanic activity or followed completely different thermal evolution patterns. If far-side volcanism ceased earlier than near-side activity, it would suggest that hemispheric differences in crustal thickness and composition significantly affected magma generation processes. Alternatively, if far-side samples also show evidence of young volcanic activity, it would indicate that the entire moon remained thermally active longer than previously believed. The Grail mission, which mapped lunar gravity fields with unprecedented precision, revolutionized understanding of lunar interior structure without returning a single sample. The gravity data revealed that the Moon's crust varies dramatically in thickness between hemispheres, with the far side showing much thicker crustal materials. This observation helps explain why far-side volcanic activity was less extensive than near-side volcanism, but sample analysis is needed to confirm the timing and characteristics of far-side magmatic processes. Orbital mapping of thorium and creep distributions showed another striking hemispheric asymmetry. Creep represents rocks enriched in potassium, rare earth elements, and phosphorus that formed during the final stages of magma ocean crystallization. These materials concentrate heavily on the near side, particularly in the region around Mare Imbrium, but remain relatively scarce on the far side. Understanding why this asymmetry developed requires detailed chemical analysis of far-side samples. Space weathering processes gradually alter lunar surface materials through solar wind bombardment, micrometeorite impacts, and cosmic ray irradiation. These processes create nanophase metallic iron, glass coatings, and welded particle aggregates that give lunar soil its distinctive properties. Apollo samples revealed how extensively space weathering modifies surface materials, but far-side samples will show whether different exposure conditions create different alteration patterns. The impact history preserved in lunar samples provides crucial information about the bombardment history that affected all inner solar system planets, including Earth. Lunar rocks contain detailed records of impact events that help scientists understand when the heavy bombardment period ended and how impact rates have varied over geological time. Far-side samples from the South Pole Aitken Basin could provide evidence of the largest impact events in lunar history. Sample analysis techniques have advanced dramatically since the Apollo era. Modern instruments can measure isotopic compositions with precision that exceeds Apollo-era capabilities by orders of magnitude. Electron microscopy reveals structures and textures at nanometer scales. Mass spectrometry can detect trace elements at parts per billion concentrations. These analytical advances mean that Chang'e 6 samples will yield information that couldn't be obtained from Apollo materials using 1970s technology. International collaboration in sample analysis ensures that the scientific benefits extend far beyond any single nation's research programs. Chang'e samples will be studied using the world's most advanced analytical instruments, bringing diverse expertise and methodological approaches to bear on common scientific questions. This collaborative model has historically produced the most comprehensive and reliable scientific results. Each new lunar sample forces revisions to textbooks and scientific models, a pattern that began with Apollo and continues through Chang'e missions. The Moon consistently surprises scientists, revealing complexity and diversity that exceeds expectations based on its small size and apparently simple structure. Chang'e 6 represents the latest chapter in this ongoing story of discovery. The accumulating collection of lunar samples from different locations and geological settings enables comparative studies that weren't possible when samples came from only a few Apollo and lunar landing sites. Understanding how lunar materials vary across different terrains, ages, and geological processes requires the broad sampling coverage that multiple missions provide over extended time periods. Chang'e 6 samples are already generating excitement in the scientific community because they represent the first far-side materials available for detailed laboratory analysis. Whatever they reveal about far-side geology, resource distributions, and evolutionary history will add new chapters to the lunar story that began with those first Apollo samples over 50 years ago. Part 10. Moon Mysteries, Gotchas, Anomalies, Hoaxes, and What We Learned the Moon has a peculiar talent for generating viral mysteries that capture public imagination while simultaneously demonstrating why careful scientific investigation matters more than speculation. China's far-side exploration missions have provided perfect examples of how tantalizing anomalies usually have mundane explanations, but only after proper investigation. In January 2020, the U-22 rover spotted something unusual in a small crater on the lunar far side. Images showed what appeared to be a cube-shaped object on the horizon, immediately dubbed the Mystery Hut by Chinese media and generating worldwide speculation about artificial structures or unusual geological formations. The rover spent months navigating toward the object, building suspense with each approach image. The Mystery Hut turned out to be a perfectly ordinary boulder, roughly rabbit-shaped, sitting on a crater rim. The cube appearance resulted from low image resolution, unusual lighting angles, and the human tendency to impose familiar patterns on ambiguous shapes. This incident perfectly illustrates how distance, lighting, and limited data can create mysteries where none actually exist. A similar pattern occurred with U-22's discovery of a gel-like substance in another small crater. Initial images showed unusual material with different reflectance properties compared to surrounding soil, generating speculation about organic compounds, impact, melt, or unknown minerals. Detailed analysis eventually identified the material as impact melt glass, a common product of meteorite strikes that creates glassy substances when rock melts and rapidly cools. The Compton-Belkovich complex on the lunar far side represents a genuine anomaly that has withstood scientific scrutiny. This feature shows evidence of unusual silicic volcanism, producing rocks with chemical compositions that are rare on the Moon but common on Earth. Unlike the Gel and Mystery Hut, this anomaly has proven scientifically significant, revealing previously unknown aspects of lunar geological diversity. Water detection on the Moon illustrates how scientific understanding evolves through improved methods and accumulated evidence. For decades after Apollo, scientists believed the Moon was essentially bone dry. The Apollo samples contained virtually no water, and lunar formation models suggested that any primordial water should have been lost during the Moon's violent origin. This dry moon paradigm dominated lunar science for over 30 years. The paradigm began shifting in the 1990s when orbital missions detected possible hydrogen signatures near the lunar poles, suggesting water ice in permanently shadowed craters. However, hydrogen signatures could also indicate other compounds, and the evidence remained ambiguous for years. Only when NASA's L-Cross mission deliberately impacted Cabeus crater in 2009 and detected water vapor in the debris cloud did scientists gain definitive proof of lunar water ice. Subsequently, India's Chandrayaan-1 mission and NASA's Moon Mineralogy Mapper detected water and hydroxyl signatures distributed more widely across the lunar surface than anyone had expected. China's Chang'e 5 samples provided direct measurements of water content in returned materials, confirming that lunar rocks retain more water than Apollo-era analyses had suggested. Helium-3 represents perhaps the most persistent example of speculation outpacing scientific reality. The concept of lunar helium-3 as fusion fuel has captured imaginations for decades, inspiring science fiction stories, research papers, and exploration advocacy. While the basic science is sound, helium-3 exists in lunar soil at concentrations measured in parts per billion, and fusion using helium-3 remains technologically undemonstrated. Responsible science communication requires distinguishing between established facts, reasonable hypotheses, and speculative possibilities. Helium-3 fusion falls into the speculative category because it depends on technological developments that haven't occurred and may never occur. This doesn't make it unworthy of discussion, but it requires appropriate caveats about uncertainty and timeline. False firsts represent another common source of confusion in space exploration reporting. Chang'e 5 wasn't the first mission to detect water on the Moon, but it was the first to measure water content in returned samples. Chang'e 6 isn't the first mission to study the lunar far side, but it is the first to return samples from the far side. These distinctions matter for accurate historical record-keeping and proper credit attribution. Media literacy becomes crucial when evaluating claims about space discoveries. Extraordinary claims require extraordinary evidence, peer review, and independent confirmation before they should be accepted as established fact. The scientific process includes mechanisms for error, correction, and verification that take time to operate but ultimately provide more reliable knowledge than initial speculation. Anomalies serve valuable functions in scientific discovery by forcing researchers to develop better instruments, refine theoretical models, and test assumptions that might otherwise remain unexamined. The mystery hut and gel substance investigations, while ultimately anticlimactic, demonstrated rover capabilities and analytical techniques that will prove valuable for future exploration. Sample return missions provide the ultimate ground truth for resolving orbital mysteries and internet speculation. Remote sensing instruments can identify interesting features and suggest possible explanations, but only laboratory analysis of actual samples can provide definitive answers about composition, formation processes, and age relationships. The pattern of lunar mysteries follows predictable trajectories. Initial observations suggest something unusual, speculation fills information gaps, follow-up investigations provide additional data, and scientific analysis eventually explains the observations through known processes. This pattern illustrates how science works, gradually replacing speculation with verified knowledge through systematic investigation. Chang's 6 samples will undoubtedly generate their own set of surprises and potentially viral mysteries as analysis proceeds. The key lesson from previous lunar exploration is that patience and rigorous analysis typically provide more interesting answers than initial speculation, even when those answers seem less exotic than the original mystery. The Moon continues to surprise scientists, but the surprises usually involve subtle complexities rather than revolutionary discoveries that overturn fundamental understanding. Far-side samples might reveal unexpected mineral assemblages, unusual volcanic compositions, or distinctive space weathering patterns, but they're unlikely to contain alien artifacts or revolutionary new physics. Part 11. Who owns the Moon? The new rulebook for a new gold rush. The question of lunar ownership becomes increasingly urgent as multiple nations and private companies plan permanent installations, resource extraction operations, and territorial claims. The legal framework governing lunar activities traces back to a 1967 treaty negotiated during a completely different era of space exploration, creating ambiguities that modern missions are forcing the international community to address. The Outer Space Treaty of 1967 establishes the fundamental principle that no nation can claim sovereignty over the Moon or any other celestial body. The treaty declares that exploration and use of outer space shall be carried out for the benefit of all countries and requires that space activities be conducted for peaceful purposes. These principles remain the bedrock of international space law, but they were written when only 2 nations had space capabilities. The Artemis Accords, signed by 56 nations as of July 24, 2025, attempt to provide more specific guidelines for lunar activities while remaining consistent with the Outer Space Treaty. The Accords establish norms for safety zones around landing sites, transparency in mission planning, protection of heritage sites, and utilization of space resources. Notably, China and Russia have not signed the Artemis Accords, instead pursuing alternative international partnerships. China leads the International Lunar Research Station initiative, partnering with Russia and other nations to develop lunar capabilities outside the Artemis framework. This parallel approach creates a bifurcated international system for lunar exploration, with different nations following different sets of operational guidelines and partnership structures. The critical legal question involves resource utilization rather than territorial sovereignty. While the Outer Space Treaty prohibits national appropriation of celestial bodies, it doesn't explicitly address whether nations or companies can extract and use materials they collect. Most legal experts interpret the treaty as permitting resource utilization while prohibiting permanent territorial claims, but this interpretation has never been tested through actual large-scale operations. Safety zones represent a practical compromise between operational needs and legal constraints. The Artemis Accords recognize that landing sites, mining operations, and scientific installations require temporary exclusion zones to prevent interference and ensure safety. These zones are explicitly temporary and operational, rather than permanent territorial claims, but the distinction could become contentious as lunar activities expand. Commercial companies face additional legal uncertainties because the Outer Space Treaty primarily addresses national governments rather than private entities. Several nations have passed domestic legislation authorizing private space resource utilization, but these national laws must operate within the constraints of international treaty obligations that governments cannot unilaterally modify. Future helium-3 mining operations, if they become practical, will need to fit within this evolving legal framework. Large-scale resource extraction could strain current legal interpretations, particularly if operations require extensive infrastructure development, long-term territorial control, or export of valuable materials back to Earth for commercial sale. Environmental protection represents another emerging issue in lunar law. While the Moon lacks ecosystems in the terrestrial sense, scientific sites, heritage locations, and areas of particular research value may warrant protection from industrial activities. The Artemis Accords acknowledge this principle by calling for protection of outer space heritage sites and scientifically significant locations. The enforcement mechanisms for lunar law remain largely theoretical because no comprehensive international authority exists for governing space activities. The Outer Space Treaty makes governments responsible for their national space activities, but coordination between different national regulatory systems requires bilateral agreements and voluntary compliance rather than centralized enforcement. Looking ahead, lunar law will likely evolve through practical precedents set by actual operations rather than comprehensive treaty revision. The current international system adapts gradually to new circumstances, with customary practices eventually gaining legal recognition through consistent state behavior and international acceptance. Resource-sharing experiments could reduce potential conflicts by demonstrating cooperative approaches to lunar development. Shared communication relays, landing pad infrastructure, power generation systems, and emergency support capabilities could create mutual dependencies that encourage peaceful cooperation rather than competitive territorial control. The stakes for getting lunar governance right are substantial. Effective legal frameworks could enable sustainable economic development that benefits multiple nations and organizations. Inadequate or conflicting legal systems could lead to disputes that undermine space exploration progress and potentially extend terrestrial geopolitical tensions into space. Chang's 6 samples contribute to these legal discussions by demonstrating the value of lunar materials and the feasibility of resource extraction operations. As sample analysis proceeds and reveals information about resource distributions and extraction possibilities, the legal frameworks governing lunar activities will need to evolve to address practical realities rather than theoretical scenarios. The ultimate challenge for lunar law involves balancing competing objectives, encouraging investment and development, ensuring peaceful cooperation, protecting scientific values, and maintaining the principle that space exploration benefits all humanity. These objectives sometimes conflict, requiring negotiation and compromise among stakeholders with different priorities and capabilities. Current legal frameworks provide sufficient guidance for current lunar activities, but they will need refinement as operations expand and become more permanent. The next decade of lunar exploration will likely establish precedents and practices that shape space law for generations, making current legal development efforts crucial for long-term success. The Moon represents humanity's first opportunity to establish governance systems for permanent extraterrestrial presence. The legal principles developed for lunar activities will likely influence how humanity approaches resource utilization, territorial organization, and international cooperation throughout the solar system. Part 12. Powering a moon base. Establishing reliable power systems on the Moon presents engineering challenges that make terrestrial energy problems seem straightforward by comparison. The lunar environment alternates between weeks of continuous sunlight and weeks of absolute darkness, experiences temperature swings from 127 degrees Celsius to minus 173 degrees Celsius, and offers no atmospheric protection from radiation or micrometeorite bombardment. Solar power systems provide the most mature and well-understood option for lunar energy generation. Unlike Earth-based solar installations that must account for atmospheric absorption and weather patterns, lunar solar arrays receive direct, unfiltered sunlight during the day with no atmospheric interference. Solar panel efficiency actually improves in the cold lunar environment, potentially generating more power per unit area than equivalent terrestrial installations. The lunar poles offer particularly attractive conditions for solar power generation. Crater rims near the South Pole receive nearly continuous sunlight throughout the lunar year because the Moon's rotational axis remains nearly perpendicular to its orbital plane. These peaks of eternal light could support solar installations that operate continuously without requiring extensive energy storage systems. However, locations away from polar regions must contend with the 14-day lunar night, requiring either massive battery systems for energy storage or alternative power sources during dark periods. Current battery technology would require prohibitively heavy installations to provide continuous power throughout the lunar night, making nuclear power attractive for missions that cannot locate near permanently illuminated sites. Small nuclear fission reactors, based on concepts like NASA's Kilopower project, offer steady baseline power regardless of solar conditions. These systems could generate tens of kilowatts continuously, providing reliable power for life support systems, scientific instruments, and industrial operations that cannot tolerate interruptions. Nuclear power also enables operations in permanently shadowed regions where water ice deposits might be extracted. Dust mitigation becomes critical for any lunar power system. Lunar regolith consists of extremely fine, abrasive particles that carry electrostatic charges due to solar wind bombardment. This dust adheres to surfaces, degrades mechanical systems, and reduces solar panel efficiency over time. Power systems must incorporate dust removal mechanisms or protective measures to maintain performance in the harsh lunar environment. Thermal management presents another major challenge for lunar power systems. Electronic components must operate reliably across extreme temperature ranges while rejecting waste heat in an environment with no atmospheric cooling. Radiator systems, thermal storage materials, and careful component selection become crucial for maintaining equipment within operational temperature limits. Resource utilization can supplement imported power systems with locally manufactured components. Oxygen extracted from lunar regolith could fuel combustion-based power systems using imported hydrogen. Silicon extracted from lunar materials could potentially manufacture solar panels locally, reducing the mass that must be transported from Earth for expanding power installations. Fuel cell systems provide another option for lunar power generation, particularly during periods when solar power is unavailable. Hydrogen and oxygen can be stored at relatively high densities and combined in fuel cells to generate electricity with water as the only byproduct. If water electrolysis systems operate during sunny periods, fuel cells could provide continuous power cycling using locally produced propellants. Energy distribution systems must operate reliably in the extreme lunar environment while minimizing mass and complexity. Power cables must withstand temperature cycling, radiation exposure, and potential micrometeorite damage. Wireless power transmission could eliminate cable requirements but introduces efficiency losses and technical complexity that may outweigh the benefits. Industrial operations on the Moon will have enormous energy requirements that exceed what early scientific missions demand. Helium-3 extraction, if it becomes practical, would require processing hundreds of tons of regolith per day, heating large quantities of material to several hundred degrees Celsius, and operating gas separation systems continuously. Such operations would need megawatt-scale power systems rather than the kilowatt systems sufficient for early bases. Load management becomes crucial when power generation capacity is limited and expansion is expensive. Critical life support systems receive priority, followed by essential scientific instruments, then optional activities that can be postponed during power shortages. Automated systems must be capable of shutting down non-essential operations to maintain critical functions during emergencies. Energy storage options beyond batteries include mechanical systems such as flywheels, compressed gas storage, and pumped storage using excavated lunar materials. These systems could provide longer duration energy storage than electrochemical batteries, while potentially using locally manufactured components rather than complex chemical systems transported from Earth. The power requirements for different lunar activities vary dramatically. A small robotic lander might operate on hundreds of watts, while a crewed habitat requires tens of kilowatts, and industrial operations could demand megawatts. Scaling power systems to match mission requirements while maintaining reliability and efficiency represents a fundamental challenge for lunar operations. Fusion power, including hypothetical helium-3 fusion, will not power early lunar bases because the technology remains undemonstrated even in terrestrial applications. Current lunar power planning focuses on solar photovoltaic systems, nuclear fission reactors, and fuel cells as proven technologies that can be adapted for lunar conditions with reasonable confidence in their reliability. Chang'e 6 samples contribute to lunar power planning by providing information about resource distributions that could support local power generation. Understanding where water, ice, useful minerals, and construction materials exist helps mission planners select base locations that offer multiple resources in proximity, reducing the transportation and infrastructure requirements for sustainable operations. Base power systems couple directly to resource utilization capabilities because energy availability determines what extraction and processing operations are feasible. Abundant power enables energy-intensive mining and manufacturing operations, while limited power constrains bases to essential life support and scientific activities. The power infrastructure essentially determines what lunar bases can accomplish beyond mere survival. Part 13. Looking outward. What other worlds teach us about resources? The search for resources extends far beyond our moon, revealing patterns and possibilities that reshape how we think about sustainability, exploration, and humanity's future in space. Every world we study teaches lessons about resource utilization that apply throughout the solar system, from the ice plumes of Saturn's moons to the atmospheric chemistry of Mars. Enceladus, Saturn's ice-covered moon, erupts towering water plumes from its south polar region that contain dissolved salts, organic compounds, and molecular hydrogen. The hydrogen suggests hydrothermal activity on the ocean floor, where chemical reactions between water and rock create energy sources that could potentially support life. These plumes represent a resource delivery system that brings deep ocean materials directly to space, where future missions could collect them without requiring complex drilling operations. Europa, Jupiter's ice-covered moon, harbors a global ocean beneath its frozen surface that may contain more water than all of Earth's oceans combined. The upcoming Europa Clipper mission will study this ocean's characteristics and potential habitability, but the moon also represents an enormous water resource that could support future human activities in the outer solar system. Accessing Europa's water would require penetrating the ice shell, but the quantities available dwarf any conceivable human requirements. Mars offers a completely different resource profile that includes abundant water ice, carbon dioxide atmosphere, and mineral deposits similar to those found on Earth. The thin Martian atmosphere provides raw materials for producing oxygen and methane fuel through in-situ resource utilization techniques. NASA's MOXIE experiment on the Perseverance rover has already demonstrated oxygen production from Martian carbon dioxide, proving that life support and propellant resources can be extracted from the Martian environment. The lesson for lunar exploration is that successful space operations require using local resources rather than transporting everything from Earth. The Moon serves as humanity's testing ground for technologies and techniques that will eventually enable sustainable operations throughout the solar system. Learning to extract water, oxygen, and metals from lunar materials prepares us for similar operations on Mars, asteroids, and other worlds. Resources in space include more than just materials for life support and propellant production. Scientific knowledge itself represents a crucial resource that guides future exploration and utilization efforts. Understanding how different worlds formed and evolved provides insights into planetary processes throughout the galaxy, potentially revealing new resource opportunities or environmental hazards that affect long-term sustainability. Safety resources become increasingly important as human operations expand beyond Earth orbit. Water serves not just for life support and propellant, but also for radiation shielding that protects crews from cosmic rays and solar radiation. Bulk materials like ice, regolith, or rock can provide physical protection from micrometeoroids and space debris that pose constant threats to spacecraft and habitats. The resource challenges that accompany exploration reveal common patterns across different environments. Dust poses problems on Mars, the Moon, and asteroids. Radiation affects equipment and crew health throughout the solar system. Extreme temperatures complicate operations everywhere beyond Earth's temperate environment. Developing solutions for lunar resource extraction helps address these challenges wherever humans venture. Distance compounds every resource challenge as exploration extends farther from Earth. Communication delays make real-time problem-solving impossible, requiring autonomous systems that can handle emergencies without Earth-based support. Supply missions become increasingly expensive and time-consuming, making local resource utilization essential rather than merely beneficial for economic operations. Energy resources follow similar patterns throughout the solar system, with solar power decreasing rapidly with distance from the Sun and nuclear power becoming increasingly attractive for outer solar system operations. Understanding how to implement different power systems under lunar conditions provides experience applicable to missions throughout the solar system. A note of humility accompanies all resource planning because nature consistently surprises scientists with unexpected discoveries. Enceladus's geysers were completely unknown until the Cassini spacecraft observed them directly. Europa's subsurface ocean was inferred from magnetic field measurements rather than direct observation. Mars has revealed far more water than early missions suggested, dramatically changing assessments of resource availability and potential habitability. Keeping ethical considerations in perspective becomes crucial as resource utilization expands beyond Earth. The Outer Space Treaty establishes principles for peaceful exploration and shared benefits, but these principles will face practical tests as resource extraction becomes economically valuable. Developing responsible practices for lunar operations establishes precedents for how humanity will behave throughout the solar system. Chang's 6 samples contribute to this broader perspective by demonstrating that even familiar worlds like the Moon contain surprises and complexity that exceed initial expectations. Far-side samples may reveal resource distributions, geological processes, or environmental conditions that weren't anticipated based on near-side exploration, reminding us that direct investigation often produces results that differ from orbital observations or theoretical predictions. The promise for audiences lies not just in technological advancement, but in developing sustainable approaches to living beyond Earth that could eventually reduce pressure on terrestrial resources and environments. Space resource utilization represents not an escape from environmental responsibility, but an extension of human capability that might ultimately benefit both space exploration and Earth's environment. Understanding other worlds as resource environments, rather than just scientific curiosities, changes how we approach exploration and development. Each world offers different advantages and challenges, creating a diverse portfolio of opportunities that could support different types of human activities and scientific investigations throughout the solar system. The Moon serves as our introduction to this larger story of resource utilization beyond Earth. What we learn from lunar samples, extraction techniques, and operational procedures will influence how humanity approaches resources throughout the galaxy, making current lunar exploration efforts crucial for long-term human expansion beyond our home planet. Part 14. If China's bet pays off. Scenarios for the 2030s to 2050s. The next 3 decades could witness transformations in lunar operations that make today's robotic sample missions seem quaint by comparison. But only if several technological and economic breakthroughs occur simultaneously. China's methodical approach to lunar exploration positions them to capitalize on these potential developments, though success depends on factors beyond any single nation's control. In the near term, China's Chang'e 7 and Chang'e 8 missions will test technologies crucial for their International Lunar Research Station concept. Chang'e 7 will deploy multiple rovers and landers to search for water ice and survey potential base sites near the lunar South Pole. Chang'e 8 will demonstrate resource utilization technologies, construction techniques using lunar materials, and life support systems that could operate with minimal Earth support. If these missions succeed, China and its partners could establish the first permanent human presence on the Moon by the early 2030s. Meanwhile, NASA's Artemis program aims to build crewed lunar capabilities through a series of increasingly complex missions. Private companies contracted through the Commercial Lunar Payload Services program will deliver resource utilization demonstrations, habitat modules, and scientific instruments that test technologies needed for sustainable lunar operations. If both Artemis and the International Lunar Research Station proceed successfully, the 2030s could see 2 competing lunar infrastructure systems developing simultaneously. The midterm scenario depends heavily on whether lunar resource utilization proves economically viable. Water extraction from polar ice deposits could enable fuel depot operations that dramatically reduce the cost of missions throughout the solar system. Oxygen production from lunar regolith could support expanding human populations while providing rocket oxidizer for Mars missions and asteroid operations. Construction materials produced on the Moon could build habitats, solar power installations, and manufacturing facilities at costs lower than equivalent systems transported from Earth. Economic viability requires achieving scales of operation that current missions haven't approached. A successful lunar fuel depot might process hundreds of tons of water per year, requiring mining equipment, electrolysis plants, cryogenic storage systems, and spacecraft servicing facilities that operate reliably with minimal Earth-based maintenance support. The infrastructure investments needed to achieve these scales represent billions of dollars in upfront costs with uncertain returns. The long-term scenario where helium-3 becomes relevant depends on a double breakthrough. Fusion power must mature into commercially viable technology, and lunar mining must achieve the massive scales needed to extract useful quantities of helium-3 from parts per billion concentrations. If both breakthroughs occur, helium-3 could transform Earth's energy system while creating enormous economic incentives for lunar industrialization. Fusion using helium-3 offers theoretical advantages over deuterium-tritium fusion, including reduced neutron production and less radioactive contamination of reactor materials. However, helium-3 fusion requires higher temperatures and pressures than deuterium-tritium reactions, potentially making it more technically challenging rather than easier to achieve. Current fusion research focuses primarily on deuterium-tritium systems because they offer the most accessible path to demonstrating controlled fusion power. Even if helium-3 fusion becomes practical, the mining requirements remain staggering. Extracting 1,000 tons of helium-3, enough to supply a significant fraction of Earth's energy needs, would require processing approximately 150 million tons of lunar regolith. Such operations would transform entire lunar regions, requiring infrastructure investments that dwarf current space program budgets. Geopolitical considerations will heavily influence how lunar development proceeds. The Artemis Accords versus International Lunar Research Station approaches represent different models for international cooperation and resource governance. Competition between these systems could accelerate technological development through competitive pressures, but it could also create inefficiencies and potential conflicts that slow overall progress. The aerospace industry will likely undergo fundamental changes if lunar operations achieve economic sustainability. In-space manufacturing could produce goods that are cheaper to use in space than equivalent items launched from Earth. Asteroid mining might become economically competitive with terrestrial resource extraction for rare materials. Space-based solar power could supplement terrestrial energy systems, particularly for applications where terrestrial renewable energy faces geographic or seasonal limitations. Educational and workforce implications of expanding lunar operations could be profound. Space operations will require miners, construction workers, life support technicians, communications specialists, medical personnel, and countless other occupations that currently exist only on Earth. Universities may need to develop curricula for space-based careers, while training programs prepare workers for the unique challenges of operating in low-gravity, vacuum conditions, and high-radiation environments. Climate considerations add another dimension to long-term lunar development scenarios. If Earth's climate change accelerates beyond current mitigation efforts, space-based resources and manufacturing capabilities could become crucial for maintaining technological civilization. Alternatively, if fusion power becomes widely available, either from helium-3 or other approaches, it could dramatically reduce greenhouse gas emissions while providing abundant clean energy for both Earth and space applications. The pitfalls to avoid in these scenarios include over-promising near-term capabilities while underinvesting in the foundational technologies needed for long-term success. Helium-3 extraction will not power the first lunar bases, which will rely on solar panels, nuclear reactors, and fuel cells for decades before fusion technology matures. Sustainable lunar development requires mastering life support, resource extraction, and construction using proven technologies before attempting revolutionary approaches. What audiences should watch include scientific papers analyzing Chang'e 6 samples, Artemis program schedule announcements, Chang'e 7 and Chang'e 8 mission planning, and the first successful demonstrations of lunar resource utilization by any nation or organization. These developments will determine whether the optimistic scenarios for lunar development prove realistic or whether space exploration returns to the pattern of initial enthusiasm followed by reduced activity. The scenarios for lunar development over the next 30 years span possibilities from modest scientific outposts to major industrial operations that reshape both space exploration and Earth's energy systems. The path we ultimately follow will depend on technological breakthroughs, economic incentives, international cooperation, and political will that sustain multi-decade commitments to space exploration and development. Chang'e 6 samples represent one small step in this larger journey, providing ground truth data about far-side resources and geological processes that will inform decisions about where and how to establish permanent lunar operations. Whether those operations eventually include helium-3 extraction or focus on other resources entirely may depend on what these samples reveal about the Moon's hidden hemisphere. Part 15. The takeaway. What this all means for us right now. At this moment, laboratories in Beijing are analyzing dust and rock fragments that could fundamentally alter humanity's relationship with energy, space, and our own planet. China's Chang'e 6 mission has opened a completely new chapter in our understanding of the Moon, one that began with the collection of 1,935.3 grams of material from a place no human had ever touched. The samples represent far more than scientific curiosity. They embody humanity's first direct contact with the lunar far side, a hemisphere that remained hidden throughout all of human history until we developed the technology to reach beyond Earth's gravitational embrace. Every grain of that far-side soil contains information about processes that shaped not just the Moon, but influenced Earth's early development and the formation of rocky planets throughout the galaxy. The big hope surrounding these samples centers on helium-3, an isotope so rare on Earth that most people have never heard of it, yet so potentially transformative that it could revolutionize how our civilization generates power. The vision is breathtaking in its implications. Clean fusion energy that produces minimal radioactive waste, powered by materials harvested from the moon's ancient surface where solar wind has deposited this precious fuel for billions of years. But here's the honest assessment that any responsible discussion must include. Helium-3 fusion remains a long-term possibility rather than a near-term solution to Earth's energy challenges. We haven't yet achieved controlled fusion using any fuel combination, let alone the technically demanding helium-3 reactions that would require more extreme conditions than conventional fusion approaches. The timeline for helium-3 contributing to Earth's energy supply extends decades into the future, if it occurs at all. The near-term benefits of lunar exploration and sample return missions are actually more concrete and achievable than the helium-3 dreams that capture headlines. Water ice mapping enables future missions to access life support and propellant resources locally rather than transporting everything from Earth. Oxygen extraction from common lunar minerals could support expanding human presence while providing rocket oxidizer for missions throughout the solar system. Construction materials produced from lunar regolith could build habitats, landing pads, and industrial facilities at costs lower than equivalent systems launched from Earth. The global cast of characters pursuing lunar exploration creates a remarkable renaissance in space activities. The United States pushes forward with Artemis missions aimed at returning humans to the moon. India demonstrates precision landing capabilities near the lunar South Pole. Japan achieves pinpoint navigation that enables access to previously unreachable scientific targets. China methodically builds capabilities through increasingly sophisticated robotic missions. Europe, private companies, and emerging space nations contribute technologies and expertise that collectively advance human capabilities beyond Earth orbit. This diversity of participants creates resilience that the original space race lacked. Where the Apollo program depended entirely on sustained American political will and funding, current lunar exploration involves multiple independent programs with different motivations, timelines, and technological approaches. If any single program encounters difficulties, others continue advancing lunar science and technology development. The rules governing this new lunar activity trace back to the 1967 Outer Space Treaty, but modern interpretations through frameworks like the Artemis Accords attempt to provide practical guidelines for resource utilization, territorial coordination, and peaceful cooperation. China's International Lunar Research Station initiative represents an alternative approach to international cooperation, creating parallel systems for lunar development under different governance structures. These legal frameworks matter enormously because they establish precedents for how humanity will behave as space operations expand throughout the solar system. The principles developed for lunar resource utilization, territorial coordination, and international cooperation will influence asteroid mining, Mars colonization, and activities around other planets and moons where humans eventually establish permanent presence. The scientific wonder contained within Chang'e's 6 samples connects us directly to the solar system's formation over 4.5 billion years ago. These rocks formed before life existed on Earth, preserving records of impact bombardment, volcanic activity, and chemical processes that shaped the terrestrial planets during their earliest development. Laboratory analysis of far-side materials fills crucial gaps in our understanding of how planetary systems form and evolve throughout the galaxy. The human story behind lunar exploration combines bold engineering vision with patient scientific methodology and healthy skepticism about extraordinary claims. The technologies required to land on the moon's far side, collect samples, and return them to Earth push the boundaries of what's possible while building on decades of accumulated knowledge and incremental improvements in spacecraft design, navigation systems, and robotic operations. Chang'e 6 samples provide the emotional and intellectual foundation for discussing lunar resources and future space development because they represent genuine scientific achievement rather than speculative engineering concepts. The helium-3 contained within these samples exists in measurable quantities that can be studied, analyzed, and understood through established laboratory techniques, even if utilizing these resources remains technically and economically challenging. The trajectory from scientific discovery to practical application often requires decades or centuries to complete. Understanding electromagnetic radiation preceded practical electric power generation by many years. Discovering radioactivity preceded nuclear power by decades. Theoretical physics often develops long before engineering applications become feasible, but the scientific foundation provides the knowledge base that eventually enables technological breakthroughs. Current lunar exploration efforts, including Chang'e 6 sample analysis, create the scientific and technological foundation for whatever space-based civilization humanity eventually develops. Whether that civilization relies heavily on lunar resources, focuses on other worlds, or remains primarily Earth-based, depends on discoveries and developments that haven't occurred yet. The promise these samples represent extends beyond energy applications to encompass humanity's gradual expansion beyond Earth as a single-planet species. Learning to extract resources from the Moon, operate sustainably in space environments, and collaborate internationally on complex technological projects prepares our civilization for challenges and opportunities that await throughout the solar system and beyond. From a handful of dust collected on the Moon's far side to potentially powering entire planets with clean fusion energy represents an extraordinary leap of imagination and engineering ambition. Whether humanity possesses the wisdom, patience, and determination to transform that vision into reality remains the greatest question of our spacefaring future. But sometimes, the most important journeys begin with a single handful of dust from a place no human had ever touched, carrying within it the seeds of transformation for an entire civilization. The story of Chang'e 6 samples has only just begun. As analysis continues over the coming months and years, these materials will reveal secrets about lunar formation, resource distributions, and geological processes that could influence human activities for generations to come. What they ultimately tell us about the Moon's far side may prove less important than what they teach us about our own capability to reach beyond Earth and grasp the impossible.